Hey everyone, it's your physics teacher, Miss Ho. In this lesson, we're just going to go through the concept of thermal expansion. Without further ado, let's begin. Let me make my face smaller. So, for this particular lesson, the objective of this is that by the end of this lesson, we will be able to describe the thermal expansion of solids, liquids, and gases, explain the expansion of solids, liquids, and gases in terms of the motion and arrangement of the particles, as well as describe the applications and consequences of thermal expansion. First of all, let's begin with the concept of thermal expansion for solids, liquids, and gases. But before we go into that, we need to recall the properties of solids, liquids, and gases. So let's look at the states of matters first in terms of their arrangement of particles. Now, this is something you've already learned before, so this is more of a recall rather than learning something new. Let me move my face out of the way first so that we can see the diagrams. Okay, and yes, it's all just something for you to recall. So if you remember what you've learned about the arrangement of particles, for solids, they're really close together and the arrangement is very, very regular. That's why we've got the term over here, regular pattern. Liquids are quite close together in terms of the particles, but their arrangement is more random compared to solids. Gases, on the other hand, the arrangement is very far apart and also very random. In terms of the movements, this is relative to the arrangement of particles, of course. So for solids, they vibrate on the spot. Liquids move around each other, while gases, they move quickly in all directions. So the diagram here shows us the arrangement of the particles, and of course, the movements are relative to their arrangements. This is not something new to you. This is merely a recall. So let's move on. Now, internal energy is a combination of the total kinetic energy, which is due to the motion of the particles, and their potential energy, which is due to the intermolecular forces. That means the forces that exist between the molecules of the particles in the body. So whenever we say internal energy of the matter, this is what we are referring to. So the internal energy is a combination of both of these energies, which is the kinetic energy as well as the potential energy. Now, when heat is provided to a system, the particles will gain energy. So the collisions between the particles increase and causes the particles to move faster. And of course, as the temperature increases, this means that the overall internal energy of the body or the system increases. Now, when it comes to the thermal expansions of these three different states of matter, so because solids have the closest arrangement in terms of the particles, the expansion is small. It's the smallest among these three states. So the molecules just happen to vibrate faster around their fixed position and they move slightly further apart. Now, for liquids, because the arrangement is not as close as solids and there's more space in between, they generally move further than solids. And we find that for liquids, the expansions tends to be almost direct to the temperature rise. Comparing liquids and solids, we find that liquids expansion is about 20 times that of solids. Gases have even further arrangement, and that's why when heat is applied, this causes the gases to move even faster and the volume increase is much greater compared to solids and liquids. Well, unless the volume is fixed. So if the volume is fixed, then you get a different property which changes. However, for this particular lesson, we're going to focus on the volume expansion. Comparing gases and liquids, we find that gases tend to have about 30 times the expansion of that of liquids. Oops. Right, moving my face out of the way. Okay, now for this slide, we will cover thermometric property. Now, what is thermometric property? Thermometric property is a physical property which changes measurably with temperature. So this property enables us to create thermometers because if a property changes and we can measure it, meaning that as the property changes when the heat is applied, so the temperature increases, or when heat is removed and temperature decreases, we find a particular property changes. So when the property changes and we can measure that, that enables us to interpolate the values of the temperature that's being measured. So this enables us to create thermometers. So let's just go through a few different types of thermometers and what their thermometric properties are. So for example, liquid in glass thermometers, which are typically mercury thermometers or alcohol thermometers. These thermometers are built based on the volume of liquid. So the volume of liquid is the thermometric property. What does this mean? So for the volume of liquid, for example, when we apply heat, the temperature increases, and we find that the volume increases as well. So if we could measure that volume of liquid, and we find that relationship between the volume change with the temperature change, that's how we can build the thermometer. So if you look at the thermometer, oops, let me move my face out of the way, right? So inside here, we have the liquid. So for example, if this is a mercury thermometer, as the temperature increases, the volume increases. So you'll find that the mercury would move along the capillary tube. So as it increases or as the volume expands, this enables us to check what the volume is. So instead of measuring volume in this particular device, we have temperature markings on it, and with this temperature scale, we're able to determine the temperature of the object that's being measured using this thermometer. Now, volume of liquid is not the only property which changes with temperature, right? So, for example, if the resistance of an electrical conductor changes with heat, this enables us to build resistance thermometers, and that's how, for example, cooking thermometers are built. So the cooking thermometer in this case uses the changing resistance of metals. So here we've got the thermometer, and we've got that long thing which you stick into the meat, for example. So as the meat temperature changes, this metal piece that's stuck in the meat would also will respond to that heat change. And as the resistance changes, this is calibrated to match that resistance. That's how we're able to measure the temperature of the meat being cooked. Pressure thermometers uses a pressure of gases. So for example, I should really move my face out of the way. Here we go. So here is, it looks like a pressure gauge, but well, it's kind of similar in the sense that this particular pressure thermometer is also used to measure pressure of gases. So when you put it, let's say you want to measure the gas, for example, and as the pressure changes, you can have a pressure gauge. And because the pressure change is relative to the temperature, instead of measuring pressure, you can have a gauge that shows the temperature instead. So as the pressure increases, that means the temperature increases. So by calibrating that temperature and pressure change, we're able to get a pressure thermometer, which can measure the temperature of the gas. Another thermometer that's commonly used is the thermocouple. Also in full, it's called a thermocouple thermometer. And this measures temperature based on the electromotive force or current that's being induced. So this is the typical kind of device that you see, which is used to measure temperature. That's a thermocouple. So you take this what we call this metal thing over here, and you put it to the object which you want to measure the temperature of. So how it works is basically it's based on the flow of current. So when there is a change in temperature, this causes the current to flow or the electromotive force to be induced. And the greater the temperature gradient, the greater the value of the current or electromotive force that's being induced. And that's how, again, through calibration, we're able to measure the temperature. Now, in this particular lesson, we're not going to go into much detail about thermometric property. But if you'd really like to learn more about the different thermometers, especially a lot of students ask about the thermocouple, I'll come out with another video to explain how all of these work. So for now, let's just move on. So the three things that make up thermometers, and here the example that's being used is the volume not volume, the liquid in glass thermometer. So here we have a picture of a mercury thermometer, which is used as the example because that's the thermometer that most students are familiar with, right? Because this is the thermometer which we use in our school labs. So the three important parts of the thermometer, well, not parts, the three important concepts that are used in the construction of a thermometer are, number one, the fixed points. So fixed points in this case refer to the 2 points on the scale of the thermometer, which have to be, which are basically the basis of which the entire scale is built. So normally we would use the steam point and ice point. So steam points are 100 degrees Celsius, and basically that's the boiling point of water, right? And the second fixed point is the ice point, which is 0 degrees Celsius. That's the freezing point of water, which means it's a temperature which water becomes ice. So why we use these 2 points is because, well, you think about it, these 2 points, these two temperatures are very easy to obtain. So if you get water and you apply heat to it until it boils, when it starts to boil, we know that temperature is 100 degrees Celsius because water boils at 100 degrees Celsius. So even without another thermometer, you just get water, you boil it, and you see, oh, it's starting to boil, you know that's 100 degrees Celsius. Likewise, for freezing ice, or in this case, melting ice. If you get ice from the freezer and you put it out in room temperature and it starts to melt, you know that it's melting at 0 degrees Celsius. So without the use of another thermometer, you know that temperature is 0 degrees Celsius. So let's say we have a thermometer without any writing on it. That means there's no calibration, no scale on it. You just get this thermometer, place it in boiling water. When it's boiling, where that level is, that's 100 degrees Celsius. You can mark it, that's 100. Same thing for the ice point. That means when the ice is melting, place the thermometer at that ice. Wherever that level is, that would be 0 degrees Celsius. Then once we have the 100 and 0, we just divide 100 equal spaces. We can build the degree Celsius scale based on these 2 points. And that's why these points are commonly used in the construction of a thermometer. That's, of course, the second concept that's very important, the scale. But all these would not be possible without the thermometric property that is being used to construct the thermometer. So for example, this mercury thermometer is built based on the changing volume of liquid. Sometimes sometimes this thermometric property may be expressed as the changing length of the liquid column. Either way, it's kind of the same thing because the volume change causes the length of the column to change, because fixed cross-section area, that means the volume would cause the length of the column when you measure it this way to change. That also counts as the thermometric property. So now we come to the applications of the expansion of solids, liquids, and gases. So in this case, applications refer to something useful. That means once we know something, of course, we got to make use of it for something that is beneficial, right? For society and for the human race. So once we know, okay, for sure, these solids, liquids, and gases are going to expand when heat is applied, we can make use of that for something that will help us. For example, thermometric property. We know that there are some characteristics which would change with temperature. And if we could measure that property, that thermometric property, we can use that to build useful thermometers. So that's why an application of thermal expansion is the thermometric property to construct thermometers. Another very useful application is the concept of bimetallic strips, which are used in thermometers and thermostats. Now, what's a bimetallic strip? My face is not moving. Okay, it's just a mouse problem or user problem. Well, anyway, yeah. So here, for example, this is a still that's taken from, well, I'll admit it, I got this from Google Images. Yeah, but if you, basically bimetallic strips are two different metals which are stuck together. So that's why they're bimetallic, two different metals put into a single strip. So they're usually found in thermometers or thermostats. And in this case, the thermostats are found in many, many devices, such as refrigerators, ovens, irons, heaters, and fire alarms. And you can see this is all heat related. So how bimetallic strips work is, because these are two different metals, when heat is applied, they're both going to expand. But different materials expand at different rates. So because they're stuck together and because of the different rates of expansion, you may find that they would curve. So sometimes they curve upwards or they may curve downwards depending on which metal expands more. And when they cool down, they will definitely curve in the opposite direction. So through the curve, whoops, let's put it this way, through the curves, right? That's how sometimes when you have an iron, sometimes it's like you find that, oh, sometimes it will heat up, sometimes it cools down. That's because the bimetallic strips would basically curl up or curl down to connect or disconnect the circuit, depending on whether heat is needed or not, right? If you'd like to know more about how bimetallic strips work, I will also create another video to explain that. But for this particular lesson, we're just here to learn this in a quick overview. Another application would be the use of heat to create rivets. It's not my face. My face in the middle. Right. So, for example, if you find that for these kind of joints, they're known as rivets. And how come they're so secure and how do they work? So basically, a hot rivet is driven through the hole in the plates because when it's hot, it's going to expand. So one end of the rivet is then hammered in, and when they're left to cool down, the rivet contracts, and that holds the plates tightly together. Hot air balloons also work using the expansion of gases. So basically, when you've got gas inside the hot air balloon, and you always got the burner to heat this up, right? So when the air in the balloon is heated, gases, the volume would expand, and this causes the density to decrease, because if you recall, density is mass divided by volume. So when the volume increases with the same mass, the density decreases. So a lower density, of course, causes the hot air balloon to rise. Some of the consequences of thermal expansion. So in this case, consequence refers to the negative effects of thermal expansion. So application would be basically, we know that the thermal expansion could be used for good, but consequence is something that in this case we cannot control, because it's an effect that we can't control, and sometimes the effect can be quite negative. So, for example, on hot days, the roads and bridges, or even like railway tracks, could expand. And if there's no allowance given for the expansion, that's why roads and bridges sometimes it can crack. So that's why you find that for a lot of the, like all these kind of railway tracks, bridges, they tend to leave gaps in between too. That's what they call, that's the expansion allowance, so that on a hot day they can there's space to expand without any buckling or any cracking. The same way, liquids also expand, and as you recall, liquids expand even more than solids. So, almost all liquids expand when heated and contract when they're cooled. So this is why drink factories need to allow space when they fill up bottles or cans. So that's why when you buy, you see, oh, there's a little bit of space. So it's not that they're being stingy; they're just giving, expansion space allowance. Because if there's no allowance, it would cause the liquid to burst out of the bottles or cans. I realize now that yes, this recording tends to put my face all over the place. But you know what? Last one. All right. So we know that gases expand even more than liquids. Yeah. So they expand when heated, contract when cold. Okay, the expansion and contraction much greater than solids and liquids for the same volume, for the same change in temperature. And that's why we should not pump car tires to maximum pressure on hot days, because if it's maximum pressure and it's hot, it's going to expand, it can cause the tires to burst. So this brings us to the end of this lesson. This is just a brief lesson to give you an overview of thermal expansion. So if you found this video helpful, please help me out by supporting me and visiting me on at my coffee website at ko-fi.com/physicsrocks. Of course, either way, whichever the case, feel free to subscribe for more lessons, solutions, and exam strategies. Do check out more information at my website, physicsrocks.com. I hope you found this video educational and helpful. Don't forget, you gotta click subscribe. Ooh, this side. Subscribe, like, and happy studying.